Hello there. Okay, so we're gonna move on to our series, which is, I'm solving past 6 months Amazon tagged questions, starting with the easy and the most accepted one. So then the third question that I'll be doing is range sum BST. So BST stands for binary search tree, obviously, right? And our goal is to find the range sum. So basically, this problem will give us the left and right range inclusively. So what this means is, for example, if I have, so this tree, right? So this is given an array, but we can visualize it using the Leetcode's tree visualizer. So if you can click here, then you'll see the tree. You can drag it around, but you cannot see it properly because of my theme. So I'm just gonna turn this off and move it to my drawing. So for example, if my range was 7 and 15, like in the example, then my goal is to find the sum of nodes, which is ranged from 7 to 15. So this answer would be 32 because we have 10, 7, and 15. So 5, 3, and 18 doesn't count because it's not within the range, right? Okay, cool. So to do this problem, we're gonna do it with two approaches. One is using recursion. The second is using stacks. So when we're trying to solve a tree problem, usually, like most likely, we'll be using recursion, but like every problem doing recursion, it can be solved by using stacks. Like, I mean, not stacks per se, but using while loops. So that's the reason why I'm gonna do it with both, because with while loops, I just think it makes more sense than recursion, because recursion is typically really hard to visualize, hard to come up with, and it's a difficult process. But I'm gonna walk us through the problem. Okay, cool. And the biggest thing about recursion is oftentimes, it propagates really quickly and people have really hard time visualizing the situation. So what I like to do is just think of this. Imagine you have this function called helper, right? And then the input is uh, like a root, not root, just a node, all right? Just a tree node. And this helper function, what it does is it returns uh, the sum of tree nodes. So basically, it's um, our problem is to find the range sum, right? Okay, so I'm just gonna simplify the problem and then say just forget about the range. We're gonna try to find every value that we have in here. So let's just simplify the problem that way. So imagine that we have this helper function which returns all the node sums within this tree node, all right? So by using this function, how would you solve this problem, right? And then some of you will just say, hey, dummy, we're just gonna solve it by passing tree node of 10 into here, and then we'll have, I think the sum was 58. 58, that's easy, right? Okay, genius. I didn't mean literally, but how would you solve this problem with the help of this function, not using it directly, all right? So, because that would just be cheating, right? So, what I mean is try to imagine we cannot use it directly on this node, but on the children's, all right? So, how would you do that? Let's imagine we have the sum of this and the sum of that, right? So we're just gonna call this like um, sum of L. This is sum of R, right? So our helper function of 5 would return all of these sums. So that means 12, 15. Our helper function of 15 would give us all of this sum, which means it's 33, right? And then by combining these two with the top one, 10, we have 58 as the sum. So this is how you would solve the problem. So to solve tree node of 10, you would do left sum plus right sum plus your own node dot value, which these two would basically mean helper of node dot this sucks. Okay, technical problem. Node dot left, and this would be helper of node dot right, and then plus node dot val. So this literally is the solution. But let's imagine this, right? So if I'm solving this problem using this helper function, right? So I'm passing helper to this, right? And then this thing will use the helper again to solve for this. So this called that, this called that, and then this node will try to call nothing, right? Nothing. So that's the stopping point. So in every recursion, there's supposed to be a base case. Otherwise, it will just go on forever, right? So our base case is if we have a node that is null, then return 0, basically. So that's our base case. Okay, so we have the base case, we have the recursion equation, which is this thing right here. Now we are ready to solve the problem. So let's just jump in and solve the easy one first. So which means we're gonna try to find every node sum in the tree. Okay, so imagine we have the helper function, right? Self, not root, I'll just say node. Okay, so if not node, then return 0. So this is the base case. This means if node is null, then return 0, right? Otherwise, what I'm going to do is node.val plus self dot helper node dot right plus self dot helper node dot left. Okay, this literally is the solution. So how I'm going to use it? I'm just going to call it and that's it. Self dot helper of root. Run code, and then as you can see, it finds every node and then actually sums it. Okay, so now we have to use the ranges. So to do that, we can either pass in L and R in here. So I'm just too lazy to do that. So I'm just going to make this as like a global function. I'll explain why I'm doing this later, but it is okay to use this as a global function. Okay, and then in here, I'm just going to check if it's in the range or not. So if self.l is less than node.val and self.r is greater than node.val, then what you do is it means it's within the range, right? So you would return this whole thing. Otherwise, what you do is you just return that without the value. So let's just run this code and voila, it's good. So let's just run it and see if it passes. Okay, so it passes, right? But we have a problem. It's a little bit slow. So why is it slow? There are basically one reason. It's because we're just, trying to look for every possible node and then just checking if this is in the range, then it's not. If it's not, then just keep on going. Then if it is, then add it, right? But there is a op- there is a way to optimize this. How? Well, it's pretty obvious, right? So basically in this example, you can cut down this tree like this and then like that. So you would solve this portion. What this means is, let's look at 10, right? So 10 is within the range, 7 and 15. That means you go to the right, go to the left, because it's within the range. So let's look at 5. Is 5 in the range? No. So 5 is less than 7, which means we don't have to go to the left, right? Because it's redundant. Binary search tree, by definition, on the left, it has to be less than the root. So which means we don't have to go to the left. But if this right is less than 15, then we can go to the right. So that's it, basically. So let's take a look at 15. Is 15 within the range? Yes. Then go to the next one. But I mean, if I think the problem says it has to be unique numbers, so you don't have to go in here because you can check it strictly greater than 15. So this doesn't have the left, so it's just stuck in here. So okay, we're just gonna add that condition and see what happens. To do that, it's a little bit complicated because you have to store some values. So let's just take this bit by bit. Now let's just do this. So I'm gonna do like left sum, right sum, and then current sum, I guess. Or I can just say current value. Okay, so if self dot r is greater than our node dot value, right? That means we can go to the right. So our right sum would become self dot helper of node dot right. If self dot l is less than node dot val, that means we can go to the left. Self dot helper node dot right. Sorry, left. Remember, just look at this diagram, right? If this root node is within, like, less than 15, then go to the right. If it's greater than left, then go to left. So this is exactly what I'm doing. If it's greater than left, just go to the left. If it's less than right, just go to the right. Okay? And then if it's within the range, I'm not going to return this. I'm going to say curval is equal to node.val. And then at the end, what I'm going to do is just sum everything. It's much cleaner that way. Right? Then run the code. Oh, curval. I think I have missed this. Okay, good. Now submit it. It's much faster. See, compared, it's like what, 60 millisecond almost difference. Okay, so this is the way to solve this question. And obviously, if you look at the solution, there is a way, but I particularly don't like the solution because, you know, this is doing nested functions. I really don't like nested functions. It's like, um, it's only Python that does that, right? It's because, I mean, doing like this function, it's more extractable and then you can use it from other functions as well. So it's like more convenient that way. So I really don't like this approach. And the second of all, that's the biggest reason, is it's using global functions. And then you might say, I am using global functions also, but this is not the same case, right? Because I could have easily done L and R and then add L and R in every of the functions. It wouldn't matter, all right? And this is appropriate to do so because this is like right passing right here, and then I'm just doing like extraction here. But this thing is just mutating constantly, right? Self.answer is our answer, and then it's mutating constantly whenever I call this DFS. This is a particularly bad practice because what if this thing was multi-threaded or something like that, right? And then what if you want to use this DFS function in from other functions, right? Just like I said before, then you would depend on one global function, and then it can just ruin everything. So it's better to pass in this value as a separate, and then it's just much cleaner and best practice that way. And to top it off, many of the interviewers will, if they ask this question, they would insist on doing this without the global function, because with the global function, not global, sorry, global variable, it's almost like cheating, right? So you just click one thing and then you do this, and then you just don't have to mutate anything. You just have to call the function and then be done with it. Using global variables is really easy, really convenient, but the interviewers would not like it. I had this situation before when I was interviewing at Amazon. So definitely use this kind of approach. You can obviously solve this with global variable first and then make some changes and then get rid of it. That's okay, but remember, try to use it without using global variables. That's all I'm going to say. Okay, cool. On to the next solution. So next solution is pretty straightforward. It's not recursion, so it's going to use stack. So obviously with the stack, you add the root, and then you do a while loop. So while stack means it's like whenever the stack has elements, you just do while loop. And then you do next node and then immediately pop it. And then if this next node is defined, right, then you do something. So what you do is, let's just call answer is 0. So I'm going to return the answer, right? So answer is, did I mess up? Okay, I think there was an indentation error. Answer is equal to next node dot val, and then I'm just doing basic DFS. So append. Oh, sorry, it's not next node. It's you have to append it to the stack. Next node dot right. I'm just gonna start. Start off with right, and then at the left. Cool. And then return answer. So let's just see what happens. So this is like adding every value of the tree. What this happens is, let's just try to undo this whole thing, and it's gonna take forever. Okay, we're almost there. All right, cool. Okay, so we have a stack, right? And then we're adding 10 first. So 10. That's not the value, that's the tree. So we are gonna pop it. So this is no longer there. And then we're gonna add the right one, and then the left one, right? And then we're gonna pop this, and then we're gonna add the right, and then the left. So we're gonna pop this, and then we're gonna add the left, right, which is null and null. So what happens if it's null, right? So you're gonna pop it, and then see immediately that this thing is null. So you just go to the while loop again, which means you're gonna pop this again, and then you're gonna see this, and then pop it. So and then add left, right, which means it's another null, right? So what this means is that you're doing depth first search, right? So you just go left, 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 and then if it's null, then go back and then traverse here, then go back and go here, go here, go there, go there, basically. So that's what it's doing. So it's a simple stack traverse of tree. Pretty straightforward. If you know graph, then this is really simple for you. Okay, on to solving our real problem. So to do this properly, we have to do the range thing again, right? So if L is if our next node dot val and next node dot val is greater, less than R, then add this. So let's just run this and see if it works. Okay, it works. And obviously this does work, but we're not pruning the tree, right? So we have to make an if statement if we want to append or not. So let's just do that. If L is node val, then we do traversal to the left. Sorry, so this one, if R is greater than next node dot val, then go to the right. Okay, so I think this works. Let me see. Yeah, good. All right, so pretty simple, pretty straightforward. Let me just try again. I think this millisecond thing is going to change when I do it again. Okay, much better. So 99.2. Okay, this is obviously luck, but whatever. Okay, so I've done recursion solution without the global variable. I mean, there was, but technically we could have avoided that really easily. But the second one is like stack solution, which I really prefer. But honestly, some tree solutions without the stack is just pretty simple too. Okay, hope you guys understood. Hope this makes sense, and I will see you all next time.